may be similar to some of the fingerprinting things that were popular several years ago. Anyway, he was also chair of the Hyperdimensional Computing Conference. Okay, so let's hear from Peter now. Thank you.
Thank you. Slide. Let's go back to the beginning. All right. Hey, so hi, I'm Peter. As was said, I am a Ph.D. student, and I work on this thing called hyperdimensional computing, which you may not have heard of, but it's actually been around pretty much as long as neural networks. It's making sort of a renaissance now that deep learning has become a mainstay, and you're going to see eventually why this is happening. But the point of this talk will be to show how you can do a lot of cool and cool learning things efficiently and robustly with hyperdimensional computing. And I'm going to use vision as a vehicle to do that because it's an appropriately difficult task to solve. So let's just first begin with what is hyperdimensional computing, because it's very mysterious with the name, but it's actually a very simple idea. And hopefully in a few minutes, you'll be pretty much on board with the idea. So the idea is to very simply take information, project it into very big spaces. Why? Because that's what happens in your brain. You project things into big spaces. I know we like, our integers and 64 bits and stuff, but that's not what a number looks like in your brain, right? It actually exists as a representation in a big space that's very robustly created, so that every time you see 3, you get back to that space and you understand what that means. I'm going to focus on one type of hyperdimensional computing. There's actually many. Specifically the basic one, which is binary strings, just because it's really easy to understand. So we're going to be talking about binary vectors, strings of 1s and 0s, generally randomly made, completely randomly constructed, that go up to let's say 10,000 dimensions. It could be more, it could be less, but generally that's the nice point where you start seeing hyperdimensionality. So what's happening when you have hyperdimensionality? So it's sort of how you have quantum and classical physics. So in quantum, you're very obsessed with what each particle is doing here. How are they colliding? Who are they colliding with? What's happening? The probability fields, everything. It's very complicated. And that's sort of what the deep architecture is like. They have all these neurons, they're all doing things, they're all interacting with each other in various ways, data's flowing through them. But just like in physics, when you zoom out, all this complication is just a ball going like this in a quadratic and hitting another ball. And that's sort of the relationship between deep learning and hyperdimensional computing. So hyperdimensional computing exists here. Deep learning exists here. And just like in physics, it's a lot more easy to understand what's happening in the classical domain than quantum. So now let's take this analogy to the brain, all right? Neural nets operate here. You have a bunch of neurons that are interacting in complicated ways. We're trying to simulate them to the best of our capabilities. But hypervectors are way deeper in. They're deeper in through the layers. They exist somewhere deep in the brain where you're taking entire modules and operating on them, or the entire brain, and not just these very specific neurons hitting in very specific ways, structured in very specific ways. And so I'll show you the transformation between the two systems. So this is your neural network. You got a bunch of neurons, they're interacting in all sorts of ways. Let's pretend that we just care about whether the neuron was activated or not when you did something. So let's say I saw a cat, just to riff off of Rachel's cat. Let's say I saw a cat, right? And this is how my neurons activated when that happened. All right, let's just organize them in a nice array, just so we could see them all and give them an ID, essentially. And then you know what? Let's forget the connections. Just get rid of them. There you go. So now you're at step C. And now let's say you see a bunch of cat images, and you assemble all your activations as such. Well, oh, I see that 1 seems to be preferable here. 0 here, it's winning the vote here. 1 here, this seems like a tie. Tie, 0 is winning here, 1's winning, or this is also a tie here. This is hyperdimensionality. We're not looking anymore at what the state of the brain was at one point, but we're looking at what it was at common points that we're interested in. Now, if you have a long string and you're randomly generating it, you're going to start approximating what's called a normal distribution, even though you're doing Bernoulli coin flips. And the reason for that is because as you flip the coin a bunch, it's really hard to get from the expected value. You expect you get half of them to be heads, half of them to be tails. The more you flip them, the harder it is to actually deviate from that halfway point. If you flip them 10,000 times, but you deviated and you have like 4,000 heads and 6,000 tails, that's somewhere over here in likelihood. About 10 standard deviations maybe. It's so unlikely that there's no way that the coin is fair at that point. And we're using that as a marker of significance for hypervectors. That's when we know that we've recognized something, detected something. So, now for some math. I know, people hate math. But this is very simple math. There's pretty much 3 things we care about with hypervectors. Our goal is to define an algebra, which is a fancy math way of saying I need to multiply and add to do stuff. So we're going to come up with ways of multiplying and adding. First one, XOR. If you're not familiar with XOR, it's essentially the difference operator. Are 2 things different? So if I have 2 bits and they're different, it's going to activate. It's going to get a 1. If I have 2 bits and they're the same, it's not going to activate. It's going to be a 0. It's almost like subtraction or addition. And because of that, it's a good candidate for addition here. But turns out it has some special properties that also work for multiplication. So you can use them either way here. Then you have permutation. You can permute your bits with some pattern. And you can actually apply that pattern over and over again. They like to, in math, put a power on that permutation than to say, I've permuted it this way this many times. And of course, if you know how to get rid of the way you've shuffled them to go back to the original, you can depermute them to get back to the original data. This is a type of multiplication only. You're not going to see this used for addition at all. And then finally, raw addition. But maybe a little bit different than you're used to seeing. This is what's called a consensus sum. I was doing consensus sum back here when I observed that, oh, 1's more common here. Oh, 0 is more common here. So the consensus is essentially just that. Who wins the vote in each of these to get you a new summed vector? So essentially it's a voting mechanism. And what's interesting about this, and you can throw in the random tiebreaker if they tie, that's fine. What's interesting about this is if I have one piece of data and I compare it to other things it's been added to. So let's say I'm looking at any one of these A, actually. I put an I there if you can't see it. Any one of those A's, and I XOR it with the sum of all these A's, I'm going to actually get very close to 0. Close in the Bernoulli sense, where the likelihood of it is somewhere here. It's just very unlikely to happen. So those are the basic operations, and you're going to use them to construct things because the art of hyperdimensional computing is not about like where the data comes from. It's about what you do with it. That's why we care about an algebra. And what we do with it is we make structures. Let's say you want to make a set of things. Well, you could just add a bunch of things together. So XOR is pretty appropriate there. You can just XOR your things, give them random identifiers, random hypervectors. Let's say they're called little a and little b and little c. XOR them together and voila, the result is a set. And it behaves like a set. I can tell if something's in there because if you XOR with a, it'll remove a. Right? That's how XOR works. So it's an interesting way of building and then removing things from sets. Now for sequences of things, order pairs, whatever you want to call it, you're going to make use of permutation to sort of shuffle things and represent index. So index 0 is no permutation. Index 1 is 1 permutation. Index 2 is 2 permutations, so on and so forth. And then add them up. That way you've imposed order into the structure. And then finally, records, which is a fancy name for an object. So basically, like traditional objects in Java, you have attributes and they have values. So my attributes here are A, B, C, and the values for them are X, Y, Z. So I bind, as they like to call, I bind an attribute to its value, and then I add up all the attributes that represent my object. And that's it. That's my representation of that object. With these things, we can do inference. This is just a very basic example, but you can try this yourself with random strings, and it works. Let's say I build a representation of a system for detecting birds, cats, and dogs. So let's say, just for simplicity, I give them one image of these things. Even if it's random data, I can find from either the image or the object what I'm looking for by building a record, so binding the image to the attribute, and then XORing with the thing I'm looking for. So let's say I'm looking for U, which is a bird. Well, I'm going to be very close to B. The distance between B and everything else will be basically close to 0, unusually close. And of course, if our U, V, and W are actually a bunch of images that have been consensus summed together, I start to see some patterns about what makes a dog, a bird, and a cat visually. Okay, this is what that looks like. So let's say I have a bunch of dog images. I add them together with my consensus. I can XOR them with a completely random vector to represent dog. And then I have a bunch of classes like that, and I just add those up too. And that's it. To then detect the dog or whatever. You give me an image of a dog, I XOR it with my model, this blue thing. I'm going to be very close to this. Hence detecting it. Okay, so what if we wanted to make images? Representations of images, but like not just random vectors, because that's not very useful. It doesn't give us any useful data about the image.
Can I ask a question?
Oh, sure.
So those ones and zeros, do those represent pixels in the image or not?
Well, we're about to see that, but no, for this is, you somehow obtain them. It's sort of irrelevant here. Just you got these binary vectors somehow. But yeah, your intuition is good. That's exactly where I'm going to go. Thank you for that question, because that is what we call naive image encoding. So no matter task, we can't just use random vectors, because real life, there's semantic similarity in things, and so we have to somehow capture that in our hypervectors. And the simplest way to do that for images is exactly what was pointed out. You have to embed, first of all, pixel intensity into your structure, which hopefully displays here, this video. Oh, cool. Here, I'm going to arrange my 10,000 bits into a square. This is 0. And here, I'm shuffling through all the numbers from 0, 1, 2, 3, 4, and so on. This is the difference between that number and 0. The further I go, the more random this looks. You see? And eventually, once you reach 255, this essentially looks random from the perspective of 255. So you've embedded distance into that. Where are the slides here? Yes, okay. So, this is what that looks like as a heat map. So when you're comparing the value to itself, it's a perfect match. As you go further away, it looks more and more random. This is a random vector for perspective, so you can see it. And for an image, we also need the position of a pixel, not just the intensity. Okay, let's for now assume they're grayscale, but obviously you can do this for RGB or, as well. We can use permutation to tell us where the pixel was. So you choose 2 random permutation patterns for rows and columns, and you permute as many times as you need to represent the pixel going from here to here, let's say. This will be 4 column permutations, 2 row permutations. And then just add up the pixels together. The image is just those pixels, right? So simply XOR all of your pixels together. Boom. And that's your image. This works well sometimes, but the bigger the image, the worse it works very quickly. So you need to sort of get around this combinatorial problem growth. And the answer to that is essentially sparseness. Even in the human eye, when you see stuff, it immediately gets decomposed into, as this paper notes, 10 different signals. And they're all sparse. And they're very different in various ways, convolutions or receptive fields, so on and so forth. Okay, well, let's use that idea here. Let's only look at important features of our image. For example, some sort of neuromorphic hardware that identifies things. For example, I give a few ideas here, like Laplacian or the Gaussian. It's essentially your edges of your image, right? You can use Fourier transform and throw out some of your frequencies, basically JPEG compression, right? Log polar transform to look at your data differently, and so on and so forth. And that sparsifies your data. See, this is the Laplacian of the Gaussian. You only need to encode the non-dark values. So suddenly all your pixels are reduced to just a handful that you care about. And now you can encode your images much better. One paper I had used a special type of camera. It's called a DVS. It sees not pixels, but what are called events. And they can occur asynchronously. It's essentially each pixel is its own camera. You can think of it that way. And you're just seeing what happens over time on each of those cameras. And so they like to see motion. So as you're moving, you might see something like this, where in reality it looks like that. Or if you're standing still and people are moving, you'd see this. Well, turns out you can turn these into images pretty easily. This is the work of a colleague of mine. He shows you how you can sparsify your events to only focus on the interesting stuff. So you can make images out of them. And this is an example of what you might see for an image. And now, I can use these with hyperdimensional computing to navigate a drone with about a couple megabytes of data, 1 CPU, and actually, in our experiment, we needed like 15 seconds of data, and we matched a CNN. That's a big deal. Now, how do we do that? Pretty easy. The drone moves, it sees events. We turn them into these special images, okay? We turn those into hypervectors with the image encoding per pixel technique. And then we combine them with random vectors that represent the velocity we're experiencing at that moment. Add them up together. And that's it. We formed an experience, essentially. An experience the drone had a memory of it navigating something. This is just describing that process more formally in case someone's interested. Here's an example of what this looks like. So this is the angular speed of an autonomous vehicle, so basically as it's turning. And yellow is how well we're able to match it. And this is the sort of probability field across time. And you can see the attention is sort of where you want it to be, the velocity you want to experience. Yes, I said attention. It's very similar, actually, to attention in LLMs. This is for movement on the z-axis, so going up and down, and x-axis for forward propelling. It works about as well as a full CNN trained for all the data, probably a day or so of training with GPUs and everything. This is also results if someone wants to see them. They're not very important, but they're there. So hang on. I did the thing that a CNN did with 2 megabytes of memory, a CPU, and I can do it. I can predict things like 1,000 times faster than the CNN. Why is no one using this? Good question. It is catching on. As I said, hyperdimensional computing is going through a bit of a renaissance. So people are catching on that this is relevant here. Why? Well, this is where I plan to end, but I think we'll go into this topic super quick. It's catching on because you can use deep neural networks as your encoding. You don't need to do pixels. You can use the features from a neural network. So postpone the encoding process of the hypervector as late as possible. Let your neural networks handle it. Heck, you can have many neural networks doing it for you. You can add new neural networks as you go. They're all fine. Bootstrap your hypervector model with that. And what happens is something like this. The hypervector model, as it's observing the network and learning from it, will actually get to the optimal performance before the neural network. These are 2 separate neural networks. This one's a much better performing one. But as you can see, even quicker, the hypervector is at where this network will eventually end up, about 0.7%, or sorry, 70% accuracy. That's crazy, right? So why is no one using this? They're getting there. People are catching on to it, but it's still in the baby stage of its renaissance. So, people are catching on to it, but it's not fully there. This is all observed in a paper where, if you want to look at it, it's called HD glue, hyperdimensional glue. So this is a process for being able to take neural nets and just smashing them together in hypervector models. Bam. Yeah, you can take as many neural networks as you want, put them together, you're done. So, if you're interested in this, there is a link here that you can follow to keep up with people in HDC and what they're doing. And here are the papers that I referenced here in case you're curious. Most of these are mine, but this is sort of your seminal paper on hyperdimensional computing. If you're interested in seeing it from first principles, Canero is a good source. And that's pretty much it. Back to, any questions? Yeah, I guess I'll let you handle the question.
All right, this guy raised his hand real quick.
You showed an example of classification.
Yep.
So how do you train it? How do you find the prototype for classes? I'm just curious.
By prototypes, do you mean the labels?
No, you don't labels, then you need to find the hypervector.
The data itself.
Represents the class, right?
Yeah, so
how do you do this?
just like in, sorry, let me get that. Just like in deep learning, they're given to you as training data, and you're essentially turning them into hypervectors, and then you just add them up. That's how you get the prototypes. The prototype is the sum of all your examples using consensus sum. It's what all of them agree on. The vector they all seem to agree on for that class. Does that answer?
Yeah, so you're saying if the dimension is high enough, so there wouldn't be collision, right?
Yes, yeah.
That's the trick.
Yes, that's the trick. Yep, exactly, perfect. Other questions?
autonomous like driving, what other industry cases can be applied?
Pretty much anything deep learning can do. And also any other architectures that are out there, because you can use them all in this paradigm. It's been used in pretty much every type of AI you can think of. Someone's wrote a paper in HTC on it. It's just not very well known. So pretty much anything. Some of the things I've used it for is, as you saw, autonomous vehicles. I've used it for just basic classification tasks that you see from deep learning. And I've also recently been working on manifold stuff with it, because manifolds are an interesting question with hypervectors. But pretty much anything you can think of, it works with.
Okay, I just have like a follow-up. So remind me again from your like discussion why it's not really been used today.
So it was invented in the 80s, along with neural networks. It's essentially a simplified neural network. But back then, neural networks were not good enough yet to give you the kind of features you're looking for. It's not until CNNs came in that the issue of vision sort of,
Hardware, right?
and hardware, yes, hardware.
It's expensive to
It's
make
expensive.
the hypervectors. It used to be a
It used to
lot
be.
more expensive.
But now it's
Now,
Now it's not.
like the
It's
hardware
better.
is caught up considerably.
okay.
Yeah, that's another reason. Yeah.
Okay, in the interest of time, we're going to take a 5 to 10 minute break now. Obviously, Peter will be here if you want to
Yeah, you
ask
can
any
just come up.
questions. And then we're going to come back here for Yoshibak, so thank you.